My name is Matthias, and today we're going to review EKG lead placement and an axis approximation of heart depolarization. To begin, let's take a look at our leads. There's 4 leads, one on each shoulder and one on each ankle. And by alternating which leads are negative and positive, we're able to determine axes by which electrical activity is detected throughout the body. The first axis is lead 1, and this goes from the right shoulder to the left shoulder. The second axis is lead 2. This goes right shoulder down to the left foot. And the third axis is left shoulder down to the left foot. In addition to these 3 main leads, there's 3 augmented leads that allow for a pickup of electricity in between the axes of our primary leads. So we have AVF that functions from the very top of lead 1 down to the foot, AVL, which points to the left shoulder, and AVR, which points to the right shoulder. However, when trying to decipher the electrical path in the heart, depicting the electrical activity as it is anatomically detected isn't the most useful way of doing things. So we often see a demonstration in which it's on a radial plane. However, let's quickly review how we get from the anatomical position over on the left to the radial depiction on the right. It's quite simple. Because each one of these activities is a vector, every one of these arrows can be translated so that the origin of the arrow is at the center of the heart. This is done as so. And we can see is that as each one of these electrical axes are finally translated, it forms this radial graph. So now any electricity moving along the horizontal plane will be detected by lead 1. And any activity moving in the vertical plane will be detected by AVF. And all of the other leads in between detect angles at 30-degree increments. So let's take a look at an EKG quickly. This, on the left, is a standard 12-lead EKG, with the frontal leads depicted on the left of it, and V1 through V6 being the precordial leads. For the purpose of axis determination, we're not going to be too concerned about the precordial leads, so we can go ahead and ignore those for now. But if we take a closer look at leads 1, 2, 3, AVR, AVL, and AVF, there's a couple strategies we're going to use in order to approximate the axis of depolarization. The first of these is we're going to look for some overarching visual clues. The most important is to look for an equiphasic depolarization. What this means is we're going to look for patterns on the EKG in which there is an upward spike that is equal to the downward spike. In this EKG, that's demonstrated with AVL. Why might this be important, you might ask? This is because electrical activity is detected when it's moving along the path of one of the leads. So for example, if we look at our radial diagram to the right, and if we imagine lead 1 for a moment. On lead 1, if there's any electrical activity moving towards or away from the lead, it will be detected on the EKG. However, there's one condition in which lead 1 will not detect any motion, and that condition is when the electricity is moving perpendicular. So if the electricity happens to moving perpendicular to lead 1, so straight up or straight down, there's no path of motion either towards or away from the particular lead that's being examined, in this case lead 1. So on the EKG, there will neither be a net depolarization or a net hyperpolarization. This is important because any time that we have an EKG lead that has equiphasic depolarizations, this gives us a ability to say that the depolarization of the heart is perpendicular to the lead that's equiphasic. So in this particular EKG, the equiphasic lead is the AVL lead. AVL lead is located here, and it is at negative 30 degrees. What this tells us is that the electrical path in the heart is perpendicular to AVL. In this instance, that perpendicular path is equivalent to lead 2, or 60 degrees. And you can see it is indeed a right angle there. So that's our first clue we want to look for. And that can be really helpful for determining the axis of rotation. If you have an equiphasic EKG, it's perpendicular to that particular lead. The second clue is to look for very large amplitudes. In this case, we see that lead 2 has very large amplitudes. This is important because the closer any particular lead is to the actual path of electricity, the larger the amplitude. So if you look at your EKG and you have one particular EKG lead that has large amplitudes, you know your depolarization is around or very close to that particular lead. So those are two immediate clues that we can take advantage of. A second helpful strategy for approximating the depolarization of the heart is to utilize the patterns of positive or negative deflections in every lead. It's easier to diagram this than it is to explain it in words, so let's do an example. In the following example, we're going to look at lead 1 and lead 3. And we can see if we look at lead 1, there is a positive depolarization in lead 1, which tells us that anything within 90 degrees of lead 1 is where our electrical axis is moving. So over off to the right, you can see that anything that is 90 degrees from lead 1 is now highlighted in blue. That doesn't really give us much. However, if we combine this with other leads, in our example, if we use lead 3 now, we can combine the two of these to look where the areas overlap. So in this case, we also have a depolarization, which means that we know electrical activity is moving towards lead 3. So if we highlight this on our graph, we can now see in red where electrical activity would be moving towards lead 3. Now, in order to satisfy both lead 2 and lead 3, there's only one area in which there's an intersection. That area is now demarcated in purple. So based on this approximation, we know that our path of actual electrical travel in the heart is somewhere in that purple range. And if we combine this with that equiphasic information and that high amplitude information that we got from the last two strategies, we can then conclude that the electrical axis is somewhere around this 60-degree mark. Now it's important to note that this strategy can be used for any of the leads. So now in this next example, we're going to look at lead AVR initially. And AVR is interesting in this case because it's negative. So because AVR is negative, it tells us the electrical activity has to be away from any point in that lead. So we've highlighted this now in green. You can see that anywhere in green, the electrical path would create a negative depolarization in AVR. So we're going to combine this now with lead 3. And lead 3 is positive still. So what we're going to do is we're going to shade the areas in which lead 3 would be positive. That's going to be demarcated now in blue. And you can see there's an area in which they intersect. That intersect is this red area. Now this area is larger. You can see it's not as accurate as using lead 1 and lead 3. So if you want more accuracy, you can just include more leads. So for example, if we now include lead 1 in addition, you can see from this blue shading in lead 1, we now have that original small triangle that we got when we used lead 1 and lead 3. Whichever leads you wish to use, it's only going to give you an approximation, but it can be really helpful for determining the overall axis of depolarization. In this individual, because normal is anywhere from negative 30 degrees down to 90 degrees, we would be able to confidently say this axis is normal because the overlap space is from 30 degrees to 90 degrees. There's one more strategy that's a little bit more numerical for approximating an axis. This is using some math. So to do this, there's a formula that I find very helpful. This formula is very generic, and it says that degrees of a particular lead A multiplied by the weight of that lead plus the degrees of a second lead, or lead B, multiplied by its weight, will give you the approximate total axis depolarization. So to do this, we're going to look at amplitudes. And the weight of lead A is dependent upon its proportion of the total amplitudes. So if we do this mathematically, we're going to look at leads 1 and lead 3. All we have to do is count the squares to the top of the amplitude. And we can see that for lead 1, it's 8, and for lead 3, it's 8. So then if we use this equation, we know that lead A, being in this case lead 1, has 0 degrees because it's located at the 0 degree axis. Its weight is 8 over 8 plus 8, in this case 1/2. We're going to add that to the third lead, which is at an angle of 120, and multiplied by its weight. And when we do that, we get a 60-degree depolarization. Now notice that that 60-degree depolarization is right on lead 2. And this is corroborated by our equiphasic depolarization in AVL and our large amplitudes in lead 2. So a really key step in doing this mathematical approach is to do a final logic test, where you look at your number you got. In this case, we got -60, and then you ask yourself, does this make sense? All right, let's do these approaches with one more example. And in this example, what we're going to see is we're going to look at this ectopic beat, and it's circled here in black. Now, if we notice initially, our first strategy of looking for an equiphasic depolarization isn't incredibly helpful. We only have one spike, and so we don't have a lot of information. It's possible that lead C is equiphasic, but without seeing more of these same beats, we wouldn't want to come to that conclusion. The second approach, looking for large amplitudes, would lead us to conclude that lead 3 would be most indicative. Now, lead 3 has a fairly large amplitude in the negative direction, which would tell us initially that it's somewhere directly opposite from lead 3, because again, it's negative. So based off of just looking at this lead 3 peak, we can guesstimate that it's somewhere around the -60-degree mark. However, let's try and be a little more accurate. So let's do the approach where we look at whether it's a positive or negative depolarization and shade half of our circle. So for lead 1, we know that it's somewhere in this green space. And for lead 3, we know it's somewhere in this blue space. And that puts us in this intersection area, denoted here in this turquoise color. However, we now get to look at this interesting case in which lead 2 is not incredibly helpful, but can give us some clues. So lead 2 is not strongly depolarized away or towards. It's near equiphasic. What that means is it's somewhere near the perpendicular to lead 2. Now, we don't want to be too stringent here. So what we can do is we can add large wedges that depict areas in which lead 2 would be kind of around the perpendicular. We can see here this purple wedge, I'm shading right now, that purple wedge is where there's an intersection of all 3 of these leads. So it's likely that our axis of depolarization is within that purple wedge. On an exam question, there would only be one of the answers that would fit in this purple wedge, and so using this strategy would get you to the correct answer. However, we can also use a mathematical approach. So if we do the same thing where we look at our raw amplitudes, and we use the same equations where we're using the weight of one lead and its relative degrees and the weight of another lead and its relative degrees, we can calculate an approximate axis. For this example, we can use lead 1 and lead 3 because they're very clear in their depolarizations. And we can say that lead 1 is 0 degrees. Its amplitude, I counted out as 10 units. And its weight is 10 over 14 because the amplitude of 3 is 14. Lead 3, notice I've put in a -60 here. That -60 is important because lead 3 runs in the direction of positive 120. However, we can see this depolarization, or the electrical activity, is away from lead 3. So you use -60 in lieu of 120 because it's actually on this side of the circle. And we use its relative weight of 14 over 10 plus 14. And when we do this calculation, we get a -59 degrees. Now, the actual axis of the heart is around -50. However, being 9 degrees off is within the realm of error that you would need for any clinical or exam-based answer choices. Hopefully, this was helpful for determining the axis of electrical activity in the heart, and I wish you all the best with your studies.